Okay, so we've talked about two of the forms of intermolecular forces. Those would be the dipole interactions and also the hydrogen bonding interactions. There's one last type of interaction that you're going to have between molecules, and that is what's called the London dispersion forces. Sometimes these are just called dispersion forces, and these are going to be the weakest of all the types of intermolecular forces. Okay, these are also kind of a little, probably the most complicated to describe as well. All right. So first of all, let's pretend that we don't have these delta pluses, delta minuses in there, because so far, based on what you know, we would not expect to have any of these in these molecules, because this would not normally be a polar molecule. All right. So just taking a look at this nitrogen molecule right here, is there anything that would ordinarily give it one of these a reason to stick to one of its neighbors? Okay, ordinarily we would say no. This would not be a polar molecule. We would not expect to see delta positives on this end and delta negatives down here, because these atoms would share these electrons equally. All right. The thing that happens, though, is that even if you have molecules of equal electronegativity in what we would normally say is a nonpolar bond, random electron movement, even though it's random, will occasionally cause the electrons in these bonds to temporarily be more on one side than the other. All right, and when that happens, you have a temporary situation where one end of the molecule will be delta negative and the other will be delta positive. All right, we call that condition to be a temporary dipole. All right, so even though I've drawn a delta negative and a delta positive down here, keep in mind this is a very temporary situation. All right, in the situations above, when we drew delta positives and delta negatives with a polar bond, remember that these things would be permanent situations within those molecules. All right, so what happens, though, is that if this end of the bond is temporarily delta positive, a neighboring molecule, that will cause the electrons in these bonds to be slightly attracted towards that temporary delta positive on this molecule right here. And when that pulls the electrons down here, this end becomes temporarily delta negative, and this end delta positive. And then there's a slight attraction between the delta positive on this end of the molecule right here, and the delta positive on this end, and the delta negative on this end right here. All right, and that causes a little bit of a stickiness between these two molecules. All right, so that's going to cause these molecules to have a temporary attraction for each other. The thing I want to stress about this is that this situation is temporary. Remember, it was caused originally by random electron movement, and within a matter of a very short period of time, the same random electron movement which caused the temporary dipole will probably cause the temporary dipole to disappear, and this attraction will soon after disappear. All right, so the thing about these types of forces is that they can exist in any molecules. All right, I want to contrast that with hydrogen bonding. We have to have a specific situation in molecules for hydrogen bonds to exist, but any covalent bond can have London dispersion forces. So one of the most important effects of London dispersion forces is how they affect molecules. And the most important effect that they're going to have is how they affect their melting points and their boiling points. All right. So I've shown a couple of molecules here that have a lot of similarities with each other. They're all what are called hydrocarbons, which mean they're only made up of carbon and hydrogen bonds. And all of these also only have single bonds in them. All right. We'll start off with the case where you've only got one carbon with the 4 hydrogens. All right. This is called methane. It's also known as natural gas. This one right here with the 1, 2, 3, 4, 5 carbon chain, this is called pentane. And I've drawn this as a line angle drawing because it would take a long time, but this is just like this molecule, except for their 18 carbons linked end to end. All right. So one thing I want you to notice about this is that over time, what I want you to notice is that as the number of carbons, as the size of the molecule increases, this is a very small molecule, this is a medium-sized molecule, and this is a larger-sized molecule, the boiling point consistently gets higher. All right, and what this is what this points out is that when you have a larger molecule, there are more electrons in the molecule. All right, and that means that there's going to be more opportunities for these London dispersion forces to exist. All right, so how would this affect it? If we've got a very small molecule, you have relatively little amounts of London dispersion forces going on. So that would cause a lower boiling point, which means at room temperature, this would be a gas. All right. With this particular molecule right here, its boiling point is 36. So considering room temperature is about 25, that would be... So considering room temperature is about 25 degrees Celsius, this material would be a liquid at room temperature. All right. And on this material, I showed that the boiling point is way higher than the boiling point here. But when you get this high, you start to have to worry about where the melting point is. And for this, the melting point is 29. So at room temperature, we would be below the melting point of this. So room temperature, this stuff right here would be a solid. All right. So in general, the larger the mass of the molecule, you're going to have more electrons and more opportunities for the London dispersion of forces to exist between molecules, and that overall has the effect of increasing the melting points of these things, melting and boiling points of these things, meaning that larger molecules tend to be solids at room temperature, smaller molecules tend to be gases at room temperature. Okay, so I want to sum up some of these trends here. And so we've talked about a bunch of different types of compounds and bonding. And what I want to try to do here is give you some sort of sense of, all right, given a type of molecule, would you tend to think of it as being something that would be a gas? Would it be a liquid? Would it be something that's hard to melt? Would it be something that, is very, very easy to melt? So, so first of all, let's start by just saying, recalling that in order for a solid to melt, what has to happen is that its particles must be able to slide past each other. All right. In order for things to boil, the particles need to be able to separate from each other. All right. So notice I say particles because that could either mean an atom or a molecule. But when you're looking at the structure of things, if things can totally separate from each other, it would tend to be a gas. If nothing in the structure if everything seems to be all locked together, that's going to be a solid. And if there's enough, if there's a weak enough force that they can hold together, but they can still slide past each other, that would be a gas. All right. So what would be the types of materials that would be expected to have the lowest melting points and boiling points? All right, and versus what's going to be expected to have the highest melting point and boiling point. And remember, high melting point, boiling point is the same as saying it's likely to be a solid at room temperature, whereas low melting point and boiling point are things that are likely to be a gas at room temperature. All right. Okay, so we're going to start here with the high melting point, boiling point end of the spectrum. All right, so what types of things would we expect to see there? All right, so what we've talked about this year, the things that would be the highest would be ionic compounds. All right, remember in an ionic compound, you have this alternating arrangement of cations and anions. All right, and if you look at that, and this would be like the arrangement of sodium and chlorine atoms in a crystal of salt. Is there anything in this alternating arrangement that would allow any of these atoms to slide past their neighbor. And no, I mean, these things are locked in a very stable arrangement. They don't want to move relative to each other. All right. Therefore, you would expect this to be very high melting. All right. You would have to put in a lot of energy to get these things to slide past their neighbors. All right. So let's move down to the lower melting point, boiling point into the spectrum. All right. So what are going to be the things that we would expect to be gases? All right. There's two things that we can put down there. They're basically going to be a tie. One is going to be noble gases. All right. If you think about helium atoms, all right, are these polar? No, they're not polar. They can't hydrogen bond. So none of the forces that would normally hold things together would apply here. The only type of force that could exist between these is going to be London dispersion forces. All right, the random electron movement around the helium atom could be temporarily on one side of the atom versus the other, creating the temporary dipole, which means if you get this cold enough, there is a way for these guys to have an attraction for each other. But hopefully you know that at room temperature, helium is going to exist as a gas, and that's because there's not really a whole lot of reason for these to stick to each other. All right. Another category is going to be small nonpolar molecules. The nitrogen in the air, all right, exists as nitrogen molecules. But again, the only type of force that can exist between these is going to be the London dispersion forces. All right. This is not a polar bond. I can't draw a permanent delta positive, delta negative. No hydrogen bonding is possible. So these guys aren't going to have much attraction for each other. And that's why you have to get them really cold to get them to liquefy. All right. Moving up to the next level. All right. What would be kind of between these guys? All right. So there's going to be two things which I'm going to call a tie here. And if this was a small nonpolar molecule, what's something we could do to a molecule to make it have a little bit more attraction for its neighbors? And we're going to say first a small polar molecule. All right. So classic example of this would be like water. All right. Remember, you could put a delta positive on the hydrogen, delta negative on the oxygen. And this is one of those special dipoles where it can do that thing called hydrogen bonding. All right. So what's going to be a close tie with that is going to be a large nonpolar molecule. All right. So there are no polar bonds in this. All right. But the difference between this versus this is there's just more atoms in it. And remember, the more mass there is to a molecule, the more opportunities for those London dispersion forces to exist, and that's going to have an effect of increasing the melting points and the boiling points. All right. So notice in this, we changed one thing about each of these. All right. This was small, just like this was small. We changed the polarity. All right. This guy right here, these were both nonpolar. We said that this was small and this was large. All right. Well, what if we combined those two features to have a larger polar molecule? All right. Well, that would be a molecule like this. This is glucose, all right, which is going to be chemically similar to sucrose, table sugar. And you'll notice there's a decent number of atoms that are bound to each other. And you also have all of these oxygen-hydrogen bonds all over the place, all right? And remember, each of these, if a molecule has either an oxygen-hydrogen bond or a nitrogen-hydrogen bond, it's going to have that opportunity to hydrogen bond with its neighbors. All right. So these types of things would definitely tend to be solids. All right, at room temperature. All right. But with sugar, can you heat it high enough to get it to melt? All right. Yeah, you could do that on your stove. All right. Compare that to something like an ionic compound, which we said was at the highest end of the spectrum. Even on a stove, you're not going to be able to melt this. You have to supply an incredible amount of heat to this to get it to melt. All right. So just to sum up the three types of forces, where we'd say in terms of intermolecular forces, this would be the strongest end, this would be the weakest end. The strongest type that we've talked about is going to be hydrogen bonds. All right. Remember, you have to have that special situation for that. And remember, anytime you have an OH or an NH, you can do that. Next would be dipole interactions, and third would be London dispersion forces.